Hello and welcome to this fourth installment of Learn Control with Julia, or Learn Julia with Control. Today we will talk about analysis and we will get started right away. I have VS Code up here with the Julia plugin and I will load the control systems base package. I will define a simple state space system. You can look at it in the terminal. It has two states and one input and one output. We can start our analysis of this system by computing the poles using the poles function. And here we see I use a macro in front of poles. And when I execute that line, we see that, let's clear the terminal and run it again. We see that it prints, first it prints the code and then it prints the result. So this is quite convenient if you do print style debugging. You don't have to write println, you can use this show macro. You can do the same for the zeros, and we see here that there is a pole in with a small damping here, and there is a zero in that same point. So that should be an indication that this system is perhaps not the minimal realization. And indeed, if we proceed to compute the controllability matrix, here we have done so manually. So recall we have the controllability matrix is B, and then we have A times B, and then if we had more states we would have A squared times B and so on. But if we look at this controllability matrix, we see that it looks like it's not full rank. And indeed, if we load linear algebra, we can ask about the rank, and it's rank 1. And that is not equal to the state dimension p.nx of the system. So this system is not minimal. If we do the same thing for the observability matrix, we see that looks like it has full rank, and indeed rank is 2 here. So the system is observable. We don't have to form the controllability and observability matrices ourselves. We have the functions ctrb and obsv to do that for us. If you recall from basic control course, checking the controllability of a system using this controllability matrix rank condition is numerically hard. So we might want to check something called the Gramian matrix instead. Here we can compute the controllability Gramian if we pass the symbol C. So colon C is of type symbol, which is different from a string. So this has the type string, but they behave more or less the same way. So we have the controllability Gramian, and we see this is a positive definite symmetric matrix. In this case, it's positive semi-definite because the system is in fact not controllable. If we look at the observability Gramian, we see that this is full rank. And we can compute things like the singular values of the Gramian. Here we do it of the observability Gramian, and we see that there is a large difference in the singular values. If we have loaded the package robust and optimal control, we have the function hsvd for Hankel singular values. And if we compute that, we see that indeed the system is not a minimal realization because we have one Hankel singular value that is 0. If we want, we can perform balancing of this state space system. So recall P looks like this. If we call balreal, it stands for balanced realization. We see the docstring if we hover here. We get, in this case, a reduced order system since the original system was not minimal. And then we get the Gramian of the reduced order system balanced here. And we also get the transformation matrix, that the similarity transform that takes us, in this case it's a projection since it reduces the state dimension. But this is the matrix that was used to reduce the state dimension. And on this balanced realization, we see that the controllability Gramian and the observability Gramian, they are equal. And that's indeed a property of a balanced realization. We could also call min-real for minimal realization. In this case, it will compute the same thing as a bal-real did. If we would be so, both bal-real and min-real in this case performed some kind of model reduction. We have a lot of other methods for model reduction. If we go to the documentation of robust and optimal control, we have a heading here which lists a bunch of functions for model reduction. So we can reduce the order of controllers, and we can do frequency weighted reduction and things like that. All right, now I will load a system from the demo system module. It's the Woodbury distillation column. And we can see if we ask for the doc string, we see it's a delay system. It has some delays here. We haven't talked much about delays so far, but this is a common system, multiple input, multiple output system that you see in textbooks. And we might be interested in plotting something. We might, here I plot both the Bode plot and the Nyquist plot. And I pass them both into the plot function, so that just puts them in the same plot. And we see, I hope it's large enough, we see the characteristic spiral here associated with the delay system. And we see the Bode plots here. It's we have, let's see here. Yeah. Sorry about that. We have 2 inputs and 2 outputs. It appears as if the system is larger here in the terminal. And the reason for that is, see, the size is 2 by 2. The reason for that is that this is a delay LTI system. It represents the system internally as a linear fractional transform. So in fact, some of these outputs and inputs are connected in feedback with the delay vector. Sorry about that. We can, since it's a MIMO system, we might be interested in computing the relative gain array to figure out an input-output pairing if we want to close the loop using independent SISO controllers. And we see that this is in fact rather a challenging problem to control this way, because we have quite strong couplings here off the diagonal. And that's indeed why this system very often appears in textbooks. We can also plot the relative gain array elements as function of the frequency using RGA plot. Moving on to algebraic Riccati equations. The control system package doesn't have the functions care and dare that you might be familiar with. And the reason is that whether or not it's continuous or discrete is encoded in the system here, P. So if we look at P, it's a state space continuous. So we don't need to provide that information by calling a particular function. So if we create 2 matrices, Q and R, they are just identity matrices in this case, I can call the algebraic Riccati equation with the system as the first parameter, and I get the solution to the Riccati equation here. If I want the state feedback gain, I call it LQR, but that's a topic for another video. If I don't have a system P, I just have the matrices A and B, then indeed I need to indicate whether or not it's continuous or discrete. And I do that by just passing the time evolution type as the first argument. So continuous is okay to write here, and if this would have been represented in discrete time, I would have written discrete here instead. So that should be equivalent to the previous Riccati solution. And the same applies to the Lyapunov function solvers. We don't have dLyap and cLyap, we just have Lyap. All right, now I create a new system. Here I call demo systems.double mass model. I apply a low pass filter here and I scale it slightly, and these coefficients here have been chosen by me to generate an interesting margin plot. So the margin plot is a Bode plot where we draw gain and phase margin kind of lines here. So we see this line is an indication, the length of this line is related to the gain margin, and we have the gain margin for the frequency where the phase curve crosses negative 180 degrees here. And the same for the reverse for the phase margin. We have 3 phase margins here because the gain curve crosses the gain curve crosses unit gain at 3 locations. And we see the phase margins here, 3 of them, and the frequency for the phase margins. The same for the gain margin up here. If we would have like to obtain these numbers instead of plotting, we just call margin instead of calling margin plot. We can also call delay margin to obtain the delay margin directly in seconds in this case. If P had been a discrete time system, the delay margin would have been normalized to number of samples instead. If we continue our analysis exploration, we're gonna investigate something called the gang of 4. And for that we need a controller. Here I create just a PID controller where the P, I, and D gains are all 1. And we add a time constant for a second order filter here. So this is a filtered PID controller. We see the transfer function here. We can call something called a gang of 4 plot, and that will plot us the transfer functions that are commonly referred to as the gang of 4. So we have the sensitivity function, the transfer function between input disturbances and output, the amplification of measurement noise in the control signal, and the complementary sensitivity function. We can also call a gang of 4 and see without the plot suffix and get the sensitivity functions if we want to manipulate them. And we have some documentation here. If we load the robust and optimal control package, we can call a function called extended gang of 4, and that will return to us. Let's look at the documentation. It will return the following transfer functions. So from V1 and V2 to Z1 and Z2. And that transfer function is it's a 2 input 2 output transfer function that internally has all of the gang of 4 transfer functions. So if we compute that transfer function and then plot the Bode plot, we see that we get the same 4 transfer functions here, but it's represented as a single system instead. And if we see a function being used somewhere and we wonder where does that function belong, we can call the function parent module. And indeed we see that it belongs to the robust and optimal control package, so it's a good thing I loaded that here before. If we don't want all of the sensitivity functions in the gang of 4, maybe we just want the function that is called the sensitivity function. We can call sensitivity. And if we look at the doc string, we see that this is short for output sensitivity, because we have in general for multiple input, multiple output systems, we have 2 different sensitivity functions. We have one in the output of the plant and one at the input of the plant, and they might be different. And here is some documentation indicating the names of different sensitivity functions if you want to obtain a single one. If we call Hinfnorm, in this case I call Hinfnorm2 on the sensitivity function, I get the peak of the sensitivity function. It's 1.36 and it appears on this frequency. I can plot that peak in the Bode plot. So if I just call Bode plot here on this extended gang of 4, we say I get this plot we had before. I can add a horizontal line at the peak value. I did that here. I hope it's large enough. Yep. All right. And we see that the MS, the peak in the sensitivity function, is 1.37 here. And I can also add a little point there at the particular location if I want, using the scatter command. And here as you see, I call the Bode plot without any exclamation mark. That creates a new plot. But if I call a plotting function with an exclamation mark in the end, that adds to the previous plot. So that can be a nice way to incrementally add to a plot. We can also call Nyquist plot. And here you see I said ms circles, and I provided the ms value we got from the H-infinity norm. And that plots a little circle here in the Nyquist plot indicating the inverse ms. We know that the peak of a sensitivity function is related to the inverse distance from the critical point here. I should mention also that the reason I call Hinfnorm 2 is that we have an implementation of the H-infinity norm in the control system base package that is quite fast and fast to compile, but it can sometimes fail to compute the H-infinity norm. And if you load this robust and optimal control package, we make use of a different implementation of H-infinity norm in this function, which is significantly more robust but much slower, at least for small systems. All right, so here I created F1 is a Bode plot and F2 is a Nyquist plot. I might want to plot them both together, and I can just call plot with both of these plots, and I get them side by side like this. If I would like to have them on top of each other, I would have to say layout is 2, 1. And then in this case, they looked a bit, the axes look a bit cramped perhaps, but that can be tweaked. All right. Another method or function that is nice to call when you get the new system in your hands is Dampreport. Let me readjust the windows a bit. Here we see that it prints the poles and pole pairs if they are complex conjugated, and it displays their damping ratio and the frequency and time constant and things like that, which might be nice to get a quick overview of the system. We can also, of course, also call PC map if we want to show the poles and zeros in the diagram. Another analysis method that might be useful is a function called Diskmargin, and it belongs to the robust and optimal control package. If we compute the Diskmargin, we get a number that might be hard to reason about, but it can be translated to a gain margin. So here we have an upper gain margin and a lower gain margin. It can also be associated with a phase margin and a delay margin. But perhaps more interesting is that we can plot it. And here we see an area of combined gain and phase variations that is tolerable before the system goes unstable. So we see if we have a 0 gain variation, we can tolerate a certain phase variation here. Not very much in this case, maybe 13 degrees. But if we have a large gain variation, then suddenly we cannot tolerate any gain variation and that, or any phase variation, and that should be expected. That's also partly why we like to draw this circle in the Nyquist plot rather than just looking at gain and phase margins. We really want to stay outside of the this circle because we can come up with systems that more or less fool the classical gain and phase margins too. So we can have a system that has a very high gain and phase margin, but it's still very close to unstable. All right. If you're familiar with concepts like passivity, we can plot something called a passivity plot. That's plots a passivity index, and if that's below 1, the system is passive. Here it's plotted as a function of frequency. And we see for the double mass model we created before, the system is in fact not passive. But if we pass in this first order system, that is passive because it's always, the passivity index is always below 1. And that corresponds to the Nyquist curve being entirely in the right half plane. And we have some nice theory that tells us if that we have a feedback interconnection of two passive systems, then the interconnection is also passive, and then it will be automatically stable no matter how large model errors we have in the plant model, as long as we know that the system is passive. We also have some more advanced margin functions like a normalized co-prime factor margin. If you don't know what that means, that's okay. You might be familiar with it if you have taken a robust control course. We also have metrics like the new gap metric. So this is the Greek letter ny. And if you don't know how to type that, we can go into help mode, type help $ny, and it says that it can be typed by the LaTeX code \nu, and then press tab. But if you have hard time entering such Greek letters, you can also just call the ASCII variant here. And we see that if we call this function on two systems that are identical, the gap is 0, and that's expected. And if we make the systems slightly different, the gap is now non-zero. All right. That was what I wanted to tell you about analysis. The main documentation page you reach is on control systems documentation, and we have under functions we have analysis, and here we have all the doc strings listed. You find them here. You can also go to the robust and optimal control package and look at the documentation there, and we have some functions for system analysis here that are geared more towards robust analysis. Here you'll also find things like uncertainty modeling, which you might argue is part of analysis, but that's an advanced topic I will not cover today. All right, thank you.